Imagine standing on a busy street corner in the middle of the 19th century. The air is thick with the smell of coal smoke and the persistent aroma of horses. Everywhere you look, the world is powered by muscle or by massive, hissing steam engines. These steam engines are the giants of the age. They pull trains across continents and turn the heavy looms of massive factories. But they have a problem. They are heavy, they are dangerous, and they are incredibly difficult to scale down. If you wanted to power a small workshop or a single carriage, a steam engine was a nightmare. You needed a boiler, a furnace, a massive supply of water, and someone to constantly shovel coal. This was the great technical bottleneck of the era. The world was waiting for a source of power that was small, self-contained, and ready to start at a moment's notice. The dream was to create an engine where the fire happened inside the machine, rather than under a bulky boiler. This concept of internal combustion was not exactly new, but for decades it was a failure in practice. Early attempts were more like controlled explosions that barely produced enough power to turn their own wheels. They were loud, erratic, and prone to breaking. The missing piece of the puzzle was not just about finding a fuel that burned quickly. It was about understanding the physics of how that fuel behaved under pressure. For a long time, engineers thought that simply igniting a mixture of air and fuel was enough. They were wrong. The power they were getting was weak because they were missing a fundamental step in the process. This is where the story takes a turn toward a breakthrough that would change the shape of every city on Earth. In the 1870s, a quiet realization began to take hold in the workshops of Europe. The secret was not just the spark or the fuel, but what happened right before the fire. This was the birth of the four-stroke cycle. It is a sequence so common today that we take it for granted, but at the time, it was a revelation. The idea was to use the movement of the machine to prepare the fuel. Instead of just letting the fuel burn, the engine would first pull in a mixture of air and gas, and then, most importantly, it would squeeze it. That squeeze, or compression, was the bottleneck breaker. By compressing the mixture into a tiny space before igniting it, the resulting explosion was many times more powerful and efficient. It transformed a flickering flame into a concentrated punch of energy. When this cycle was perfected in 1876, the world finally had an engine that could compete with the raw power of steam without needing the massive footprint. It was the first time a machine could be small enough to fit on a workbench or a small frame while still producing enough work to replace several horses. As this technology began to spread, it did not just change how things were made, it changed who could make them. Steam power was centralized. You had to go to the power. You had to build your factory near a coal source or a rail line. But this new internal combustion engine was decentralized. You could buy a small engine, hook it up to a fuel line or a tank of liquid fuel, and suddenly you had a personal power plant. This was the spark that ignited a new kind of economy. Small shops that could never afford a steam engine could now automate their work. Small farmers could imagine a world where they did not have to rely entirely on animal labor. The scaling of this technology required more than just the engine itself. It required a whole new system of standards and manufacturing. Parts had to be machined with incredible precision because the pressures inside these engines were far higher than anything seen in a steam boiler. This drove advancements in metallurgy and toolmaking. If the seal on a cylinder was off by a fraction of an inch, the compression would leak out and the power would vanish. As these engines became more reliable, the cost began to drop. They moved from being experimental curiosities to being the heartbeat of the modern world. The economics of the era were also shifting. The discovery of liquid fuels that could be easily transported meant that these engines could go anywhere. You no longer needed to be tethered to a coal pile. This mobility was the final wall to fall. Once you had a powerful, light engine and a portable fuel source, the idea of the horseless carriage moved from a fantasy to an inevitability. people began to see the potential for a world where travel was not dictated by train schedules or the endurance of a horse. It was a promise of total individual freedom. The ripple effects of this breakthrough were felt in every corner of society. The people who built and maintained horses, the blacksmiths and the carriage makers, had to adapt or disappear. Entirely new industries sprang up overnight to provide the fuel and the lubricants these machines required. The landscape began to change as well. Roads that were once designed for light foot traffic and hooves had to be reimagined for heavy, fast-moving machines. The noise of the city changed from the clatter of wood on stone to the rhythmic thrum of pistons. Why does this matter so much today? We are currently living through a moment that is a mirror image of the 1870s. Just as the world then was trying to move away from the limitations of steam, we are now looking for ways to move beyond the internal combustion engine. We talk about energy density, efficiency, and infrastructure, just like the engineers of the 19th century did. Understanding how the internal combustion engine broke through its own bottlenecks helps us understand the hurdles we face with new technologies like electric batteries. It reminds us that transitions are rarely about a single invention. They are about the systems that grow around them. The internal combustion engine fundamentals gave us the modern world. They gave us the ability to move goods and people across vast distances at speeds that would have seemed impossible to someone born in the 1800s. It created the suburbs, the global supply chain, and the very concept of the weekend road trip. It was a massive leap in human capability that started with a simple realization about squeezing air in a metal box. Even as we look toward a future powered by different means, the legacy of that first successful four-stroke cycle is built into the very foundations of our civilization. It is easy to look at an old engine in a museum and see a heavy, oily piece of junk. But that machine represents the moment humanity learned to package fire and carry it with them. It represents the end of the era of muscle and the beginning of the era of true mechanical autonomy. The bottleneck was real. The frustration was deep, and the solution was a masterstroke of mechanical logic that has endured for over a century. That breakthrough in 1876 did more than just turn wheels. It proved that we could master the forces of nature in a way that was compact, efficient, and accessible. It set the stage for everything that followed in the history of transportation and power. But while the internal combustion engine was busy claiming the roads, another silent revolution was beginning to stir in the background. The internal combustion engine had solved the problem of portable power, but it still required physical fuel and mechanical links to do its work. As the 1880s approached, another group of thinkers began to imagine a world where power did not come from a fire in a box, but through a silent pulse in a wire. This would lead to a new way of thinking about how energy could be distributed across entire cities. And that is how the fundamentals of the internal combustion engine broke the bottleneck and set the world in motion. Next in our timeline, we move forward to 1888 to see how the electric motor and the concept of a power grid changed the stakes once again. Join us for the next episode as we explore how this new form of energy began to challenge the crown of the engine and reshape the modern world. If you enjoyed this journey through technical history, subscribe so you do not miss the next step in the story.